In this lab, we observed a spring as it oscillated. We were able to apply the energy principle to predict the motion of the spring. Specifically, we were able to use E equals kinetic energy plus gravity potential plus spring potential. Delta E is equal to 0 when there are no outside forces acting on the system, which is true in this case since there are no other forces acting on the spring. We are able to use that kinetic energy is equal to 1/2 mv squared, gravity potential is equal to mgh, and spring potential is equal to 1/2 kx squared to solve for energy. We must first analyze the video in Tracker. First, I set the origin of the coordinate axes at the connection point of the spring and set the appropriate length of the spring. We can then run through the video and see the spring's motion as we obtain its position versus time graph over to the right, where we see that it is oscillating. We also obtain all the data points for its x and y positions, which we will later be able to use to compare to the predicted motion of the spring. We can then start editing the code to predict the motion of the spring. First, we must define the necessary constants such as g, the spring constant, and the relaxed length of the spring. In order to find these constants, we must calculate them. We know that t is the period of oscillation, which is equal to 2 pi times the square root of m over k. From our tracker video, we are able to see that one period of oscillation is 1.52 seconds. We can then use this to calculate the spring stiffness since we know that this is equal to 4 pi squared times m over t squared. After calculating this, we can find that the spring stiffness is 6.87 newtons per meter. To find the relaxed length of the spring, we know that it is in static equilibrium at its relaxed length, so F, the force of gravity, is equal to the force of the spring. We can then solve knowing that mg equals k times s, and eventually solve for L naught and find that it equals 0.127 meters. Next, we must input the values of the kinetic energy, the gravitational potential energy, and the spring potential energy. We can just input these by using the known equations of kinetic energy equals 1/2 mv squared, gravitational potential energy equals mgh, and gravitational spring energy equals 1/2 kx squared. We can then begin predicting the motion of the spring by setting the force of gravity equal to negative mg in the y direction, the force of the spring equal to negative kx times L hat, and then we can find F net by summing these two forces. We can then use Newton's second law to find the velocity of the ball and the position of the ball throughout its motion. We can then find L by subtracting the spring position from the position of the ball, L hat by finding L over the magnitude of L, and S by doing the magnitude of L minus L naught. Once we edit the code, we can then run it to find a model of the spring's motion. Over to the left, we have a model of the actual motion of the spring as it oscillates, and over to the right, we have a graph of the kinetic energy, gravitational potential energy, spring potential energy, and total energy of the spring. As we can see by this yellow line which represents the total energy of the spring, which we can see that it is equal to 0, which further proves that this model does indeed follow the energy principle. In addition to using the code to plot the energies of the spring system, we can also use the code to compare the position of the model of the spring with the spring in the experiment. Over to the right, we see a plot of the red line, which represents the experimental data in Tracker, and the blue line, which represents the predicted model. We can see that they follow the same path. For your model system, is the energy principle satisfied? Justify your answer by discussing briefly your plots of energy changes. The energy principle is indeed satisfied because delta E is equal to 0 since there are no outside forces acting on the spring. This was also shown by the graph printed from the model of the code by the yellow line representing the total energy, which was 0. Using the data you obtained in Tracker, make two separate estimates of oscillation periods, first by estimating the period of oscillation from the x position data, and second by estimating the period of oscillation from the y position data. The spring system is moving in both the y and the x direction. In the x direction, it is moving in a pendulum motion. Therefore, in the period for the x position data, we can use 2 pi times the square root of L over g, as this is a period for a pendulum motion. And from that equation, we got 1.68 seconds. In the y position, the spring is moving in a spring motion, so we are able to use the equation 2 pi times the square root of m over k, in which I got 1.52 seconds. In conclusion, this spring system was an accurate representation of the energy principle, as it had no outside forces acting on it, and therefore delta E was equal to 0.